All right, here we are for this AP free response problem involving rotation. You can see this is actually from a 1991 exam. So I guess for you, that's pretty old. For me, it's a year after I got out of high school. But anyway, here we go. We have this kind of interesting double cylinder. These are rigidly attached to each other, so they move together. So rigidly connected, but free to rotate without friction on a common axle. We've got these two masses suspended from them. So you can see that M2 is like wrapped around the outer cylinder, and M1, its string is wrapped around the inner cylinder. You can see M1, if I were to yank on this guy, it would tend to rotate this kind of counterclockwise. And if I were to yank on M2, it would want to rotate it clockwise. So they tell us at the moment, though, that the system is going to be in equilibrium. Okay, so those two torques are better balance each other out. And so we want to figure out how big M2 has to be to balance that out. So I'm going to go ahead and work that on separate paper. So I'm going to start with my force diagrams, right? And I'm going to go ahead and set it up like so. So here's M1, and here is that giant, I'm not going to draw this like, to scale or anything, but here's that big double cylinder, right? And here's M2. And so if I do my forces, then you know that we're going to have a gravitational force on M1, so it'd be M1G, and a tension pulling up, I'm going to call that T1. I'll have a tension pulling down here, T1, on the inner cylinder, and I have a tension I'm going to call T2 pulling down on the outer cylinder. Tension T2 pulling up here, M2 pulling 2G pulling down there. There's also going to be a force from the axle, right? Supporting that. I don't know, I probably ought to call it a normal force from the axle, but whatever. And actually the cylinders have mass, so there'll also be their own gravitational force. I don't know, mass of the cylinders times G, say. So there we go. So there's all my forces. I noticed that, again, the string is yanking straight down, so those tensions are straight down. Good enough, just like they pull straight up on those. Okay, let's go to, we want to find, again, the mass of this guy so that the system stays in equilibrium. If it's in equilibrium, you see what I'm going to do is I'm going to do an F equals ma for this guy, and for the rotating or wanting to rotate cylinders, I'm going to do some of the torques as I alpha is the way we're going to set this up. So take a look at each system over here for M1. Now we have to decide before we start writing our sigma F's, we have to decide which way is going to be positive. You remember that for pulley problems, right? We kind of want one direction along the motion to be positive. So we could do it around this way positive, or we could do around this way over the pulley positive. Now peeking ahead, I can see that we're going to remove M2. And when I remove M2, it's going to accelerate this way, right? So I kind of am going to make that, I'm going to choose to make that way the positive direction. So over the top of the pulley and to the left, I'm going to make positive. So that means my coordinate axis is kind of going to go along the motion like this way. I'm going to call positive. So I need to be consistent in all of my signs. So I'm going to make, so when I go to write my sigma F for M1, it's going to be forces down minus up. So I'll have M1G minus T1, right? And I need those to balance out, right? This is the, sigma F equals MA. It's going to be some of the forces is MA, but I know that I need that to balance out to be 0 because we're not accelerating yet. All right. So we can see that these two are going to balance each other out, right? Work, 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 work. Okay, same sort of thing is going to happen over here, right? If I were to do sigma F as MA for this guy, this time, again, I'm being consistent. I'm going to go up this way positive. So it'll be T2 minus T1, T2 minus M2G. And that's got to balance out to 0. Again, because we're not accelerating, we're in equilibrium here in the first part of the problem. And so all we really have so far is that this balances this and this balances this, which we knew. I'm going to make a third hash mark here, make it clear that those aren't the same as those necessarily. All right, and now I'm going to do a sum of the torques is 0. All right, that's our other situation for mechanical equilibrium. We actually have two conditions that have to be met. One is the sum of the forces is 0, and one is the sum of the torques is 0. So we're going to do that one here. Sum of the torques is I alpha. We want that alpha to be 0 to be in equilibrium. So again, I want to be consistent with my sign. So it's going to be twist this way minus twist this way. So twist this way out of the page. That'll be the torque caused by T1. So the torque from T1 minus the torque from T2. I know that the axle and MCG, these are not going to exert torques because they act at the axis of rotation. So when I do my calculations for torque, it's the next thing we're going to do R cross F. These two forces, they don't have an R value. Their R's are 0, I should say. They're acting at the axis, so they don't exert any torque. So I just have to worry about torques from T1 and T2. Again, I'm doing this way minus this way, and then these are summing to 0. The way I calculate a torque, of course, is that torques are R cross F is the formula I'm going to use. So when I do the twist caused by T1, my R is just going to be the radius of that inner cylinder, okay, which we're called R1, which is a half a meter. So we're going to say, hey, that twist one, that's going to be R1 crossed with T1, yeah? And then I'm going to have minus R2 crossed with T2, okay, because that's acting at R2. Okay, I didn't label, but this right here, that's R1. And then from here, that's R2. Okay. Now, something that we know is that when you have a string wrapped around this circular object, a disc or a cylinder or a ball, and it's under tension, it's going to come off tangent to the surface. And we know that a radius drawn to that point of tangency, we know that's going to make a right angle. Same thing here, going to have a right angle. And that means that cross product there, which includes a sine of the angle between R and F, that's going to be a sine of 90 degrees then. Same thing here, sine of 90. The sine of 90 is just 1. So I'm going to end up with R1 T1 minus R2 T2 equals 0. And since my goal here is to find M2, that's in an equation here with T2. If I can find the value for T2, life will be good. Let's see here, T1, I'm going to get from this equation here. I can see that M1G equals T1. And here I can see that M2G equals T2. So I'm going to substitute those in there. So I'll have R1 M1G minus R2 M2G equals 0. Rearranging for M2, I can see that M2 is going to be equal to R1 M1 over R2, right? Because there's a G in every term, that G is going to drop out, right? So that's it. Now they actually gave me some values for these, so I can plug values in and get an answer. I know that R1, they told me was a half a meter. M1, they told us that mass had a mass, it was 20 kilograms. And R2, they told us the radius of the outer disk is outer cylinder is 1.5 meters. So if I did that math real quick here, you'd be like, okay, that's 10 divided by 1.5, or 10 divided by 3 halves. 10 divided by 3 halves, that's 20 thirds, which would be, what is that going to be, 6 2/3? 6.67 kilograms. You say, now wait a minute, this thing was 20 kilograms. How come I only need 6.67 kilograms to balance it out? That's because it's acting this tension, right? coming from that guy pulling down, it's acting at a longer lever arm than this one is, right? It's got more lever arm. It helps it exert more torque. So the torques are going to end up balancing, even though the force is smaller here. We actually have, well, what is that? That's a third, right? That we just figured out that was 20 thirds. So that's a third of the force pulling, but it's at triple the radius. You're going to end up balancing out your torques. So that's it. That's mass M2. All right. So that's the first part. That was part A of this 1991 problem. Okay, let's move on to part B. Part B would like to know, let's see here. We're going to remove M2. So now this thing is going to start to accelerate faster and faster and faster, angularly accelerate as this mass pulls and unspools here. They would like to know the angular acceleration for the cylinders. Then we'll find the tension in the cable here, and then finally find the speed of that guy once it's fallen a meter. So let's go with angular acceleration. We're trying to find the alpha value. Okay, this is now gone. So I'm going to write some new equations here. This is still going to look like this, but now with it unbalanced, it's going to be accelerating. These forces aren't going to add to zero. So if I redo, it's okay that I'm not going to redraw everything. If I redo this, again, we're calling this way positive. So I'm still going to have, when I do my sigma F is MA, I'm going to have M1G minus T1. And my system here is just M1. That I'm looking at the forces on, just M1, times acceleration. I'm going to redo my sum of the torques for this. So if I redo that and I do my sum of the torques for the cylinders is I alpha, I only have the one torque now. I just have the torque from T1. T2 is gone. This mass is removed. These guys, again, the force from the axle and the gravitational force on the cylinders, they act at the axis of rotation. They have no lever arms, so they exert no torque. Just have the torque from T1. So that torque from 1 is equal to I alpha. All right. So that torque from 1 is, in fact, going to be R1 cross T1. It's going to be at a 90-degree angle. So again, I'm going to end up with R1 T1 times the sine of 90, which is just 1, is equal to I alpha. They did tell us the I for this guy is 45 kilogram meter squared. My goal is to solve for alpha. I'm trying to solve for this guy. So you're like, okay, well, gosh, if I knew T1, I know this is 45. I know this is a half a meter. If I knew T1, I'd be all set. So I got to come over here to this guy. You see, I could write an expression for T1. And I would get that it's M1G minus M1A when I rearrange that. And I could go ahead and substitute that over here for T1. But you'll notice that when I do that, I introduced another unknown. I don't know that linear acceleration. Now, this is the acceleration of this mass falling. You'll notice that this guy, this string, is wrapped around the inner cylinder. So however far this guy falls down, that's how far a point on the rim of this inner cylinder would advance around, right? So I can go ahead and I can link that linear acceleration of a point on the rim of this rotating object with the angular acceleration of this rotating object through the expression A is R alpha. And since we're looking at this string moving, again, we're looking at this distance along the outer rim of this inner cylinder, I'm going to use R1 there. Okay, so that's what I'm going to do. Again, all of this is rigid and solid, so it all has the same alpha. So I can substitute that in there. Now I'll have gotten rid of that. So I ended up using 1, 2, 3 equations here because I have 3 unknowns, those being, well, this modified form here, T1, alpha, and A, right? Okay, anyway, having done that, so we're just going to combine now these 3 equations, right? So doing so, let's see here. I think I'm going to substitute into this guy. Nah, let's put this in there and then let's move it into here. Let's go ahead and do that. Fine. If I substitute this A as our alpha in there, that's going to look like this. T1 will be M1G minus M1R1 alpha. Okay, I'm going to take this and put it in there. Okay, so I'm not going to shift over here until I've replaced that A. I mean, you can do this in whatever order you want. I'm just going to choose to do it this way. If I do that, now I have R1 times this mess. Let's see here. Is it okay if I do two algebra steps at once? Nah, you'd rather I didn't do that. Okay, I'm going to go ahead and distribute that R1 to this mess, if that's okay with you. So I got an R1 here, I got an R1 there. It's going to be R1 squared. Alpha equals I alpha. All right. I want to get the alphas grouped together because I'm trying to solve for alpha. So I'm going to add this to the other side. I'm going to factor out the alpha from the two terms, if that's okay with you. And then I'll divide by this bit in parentheses. Notice there's an R1. Nope, there's not. Never mind. I was about to say there's an R1 in every term, but there's not because there's no R1 in that term, in that I term. So I can't factor out the R1. Can't factor anything out of that. This is it. That's as simple as it gets. Okay, I've got values for all these. Let's plug the values in. So we've got 0.5. M1 we know is 20 kilograms. G, of course, is 9.8. Divide by 20 kilograms. R1 is a half a meter again. That's going to be squared in the bottom. And then I was 45. And so if I punch in my calculator, let's give this a try. Okay, 0.5 times 9.8 times 20, that's the top, divided by the quantity. Oops, plus 45. All right, let's give that a shot. They tell me that my acceleration is 1.96 meters per second squared for my alpha. All right. And you say, so actually that's not meters per second squared. Sorry, that would be radians per second squared, wouldn't it? That's an alpha I'm calculating. All right. All right, good enough. Okay, so that's part B. All right, was to get that value. Let me go ahead and put a box around that. Again, 1.96 radians per second squared. Now, they'd like us to find the tension. You say, well, that's going to be easy because, look, we have the tension right here already isolated. So I'm just going to take this value for alpha. I'm going to put it right back in there for alpha. So now I would get T1 is, let's put our values in. M1 is 20. Here we go. Let's square bracket that. Times 9.8 minus 20, and R1 was a half, and the alpha we got 1.96. Okay, put that in my calculator. Okay, and I got 176.4 newtons, and that's the tension in that left rope. Okay, just as a quick check, if this was in equilibrium, these forces would balance, right? This mass is 20 kilograms, so 20 times 9.8. You say 20 times 9.8. We know that's 196 newtons. You can see this tension up isn't as big. It's less than 196. So overall, the force is down. It's going to accelerate down. Do you see that? And that's what we need to have happen here. So that makes sense. Okay. And it's not going to fall. If I cut the string, it would fall at 9.8. But this has to make this guy spin up, right? And so it makes sense that it's not going to accelerate at that full 9.8. It'll be somewhat less. It'll be just this Oh, we didn't calculate it. The angular is 1.96. What would the linear be? R alpha. A is R alpha, so 0.5 times 1.196. You say, hey, gosh, that's going to be a heck of a lot slower. 0.98 meters per second squared would be the linear acceleration, right? And that makes sense because it kind of spin this big guy, heavy guy up. All right, that's parts A and B and C, actually, okay, because part C, they wanted to find that tension. So technically, I'm plugging back in there for part C. There's one part left, and that is they'd like to know what's the linear speed of M1 once it's gone down 1 meter. Now, what I want to point out is that our acceleration here, look at the values that angular acceleration depends on. R1, M1, G, and I, those are all constants. So it's a constant alpha, and we're going to have a constant A as well. So we can go ahead and we can figure out how fast it's going to be going at the end. We could just use kinematics. We've got constant alphas and A's and everything else, so we can use just normal kinematics equations to solve this. Am I really going to squeeze it in on this one page? Or am I going to go on to a second piece of paper just to do a quick kinematics calculation? Seems wasteful to waste another piece of paper for that. I'll do it. Here we go. So we could do this a couple different ways. We could start with this angular quantity, and we could change it to an A, to a linear quantity, and then do it all with linear values. We could calculate it all with angular, right? And do the kinematics with this and find an omega, right? And then from the omega, then switch over to find the final velocity, right? Okay, but because linear speed is what we're trying to find. But you know what? Since they gave us distance 1 meter, they didn't give us an angle. It's going to be easier to convert and do it all with linear values instead of angular quantities. So first thing I'm going to do is what I actually just did in passing, and that's I'm going to change this alpha into an A. And then I'm going to do it with kinematics, with just my normal linear motion kinematic stuff. So here we go. So kinematics, you say, gosh, it makes sense to make that list of variables. A, V naught, V, displacement, and time are 5 motion variables. We said A, I know that A is R alpha. Okay. And again, we want to know how far this guy's going to descend. He's unspooling at the inner cylinder, so I'm going to use that inner radius. So that's going to be 0.5, and my alpha from before was 1.96. Okay, and if you do that, I should be able to do that in my head, shouldn't I? Wouldn't that be like 0.98? Of course it's 0.98 meters per second squared. That's the linear acceleration. V naught, we're starting from rest. Final speed is what we want to know once we've descended 1 meter, right? So that's it. You say, hey, A V naught V delta X. We can use this one. V squared is V naught squared plus 2A times the displacement. That's the one that doesn't have time. And you say, okay, solving for that final velocity. Look, it's already kind of isolated for us. So you got to take a square root. V naught plus 2 times 0.98 times the descent of 1 meter. And I'm going to take a square root to get the velocity. That's going to be a square root of 2 times 0.98, a square root of 1.96. 1.4 meters per second is our final speed. Ta-da! And that's that free response problem. Okay. All right. So kind of the main idea we're using here is we're using F equals ma for each object that's translating. And then we're doing a sum of the torques as I alpha, which is our rotational analog for Newton's second law, right? It's the rotational version of F equals ma. And so we're using that on the spinning axle, right? And that's it. That's spinning pulley. All right, and then we get a system of equations that we can then solve through to find all the tensions and accelerations and such. Okay, that's it for that problem.